Uh, Welcome all of you. So we'll start the session with a meet. I will just share the screen. So am I audible to all of you?
Yes, sir.
All right. So we are going to start without further delay. So I will first introduce myself. I am Vijay Rane. I'm a Prime Minister Research Fellow in IIT Delhi, and we are here to for a problem solving session on the topic of one and two dimensional NMR spectroscopy for the chemist. I'll just So before going to the session, so does anyone have any doubt regarding the any problem in the week four? So if you don't have problem, we'll just directly go to the some of the representative problems based on uh, the topics that we have covered in the fourth week. So we are discussing the problem based on the week four, and which is like mainly covered the topic on the like chemical shift and the coupling fact chemical shifts and the coupling and the factors contributing to the chemical shift. So these are the two important topics that are covered in this week four. So that we are going to cover here. So this is just general NMR spectra, the 1H NMR spectra, that the region, which is like the x-axis is the delta values, and the zero with the zero peak stand for the tetra methyl silane, and we get the NMR spectra from the 1, 2, 3, 4 to 10 or onward in the ppm. So that we call it as a delta ppm value or the chemical shift values, which are in the ppm, and the region near to the TMS, which we call as a lower frequency region or also the shielded region. And in many cases, we also commonly call it as a upfield. And similarly, the region which is the delta value more than the 6 ppm or 5 ppm, we call it high frequency region, or the deshielded zone or deshielded region or the downfield region. Am I clearly audible, right? So this region we call it as a downfield region, and we look for some problems. Let's say we have some example of the CH3F. Then the instead of fluorine, there is attached the another group is CH3OH. Next group is CH3Cl. Then CH3Br, CH3I, and onward. So we take this example in which the group attached here for the CH3 group is fluorine, hydroxy, chloro, bromo, and iodo. And I have given here the electronegativity value. So if you look at the electronegativity of this fluorine, which is 4, electronegativity of hydroxy group is like 3.5. The chloro is 3.1. For the bromo, it's 2.8. For iodo, 2.5. And for, let's say, this is like CH3 and hydrogen. So this hydrogen, like, let's take this as a group, and which has the electronegativity value about 2.1. Similarly, if we have the silicon, then it is 1.8. So here, as electronegativity increases, the delta value or the chemical shift values are also increased. So the order will be in this manner. So the order of the chemical shift value. So this chemical shift value uh, will be in this order. So for this one, fluorine, it is 4.26. For this CH3F, it is the for this methyl 3 methyl, sorry, 3 hydrogen, the delta value is or the chemical shift value is 4.26 ppm. Similarly, for this in the methanol, that CH3OH, in this one, the delta ppm, delta chemical shift value is 3.4 and onwards for the chloro, bromo, and iodo. And similarly for the methyl, that is group for the methane and the tetramethylsilane, the electronic value is again less than this hydrogen. So the chemical shift value is in this manner. So in this way, you can solve any problem based on these concepts. And there are some problems I have saw in the assignment for. So that problem also you can easily solve based on this one. Next question is in the same concept. Here some examples are like the methane. Then another one is the chloroform. The next one is the dichloromethane, or we call it the DCM commonly. And another one is the, sorry, this chloromethane, and this is the chloroform. So there are, we have the four examples, one, two, three, and four. So the order of the chemical shift value in this one. So in the previous problem, we have seen here the effect of electronegativity, right? And in this one, here we will see the effect of number of electronegative groups attached on the carbon atom, which is attached to the hydrogen that we are looking for. So here it is effect of number of substituent. So let's consider these hydrogens uh, among this one. So all here are hydrogens. So this is the methane. This one example is CH3Cl. So one chloro group is attached. Here there are two chloro groups are attached, and here there are three chloro groups are attached. So here in this one, the number of electronegative groups are getting increases. So here there are zero electronegative groups, right? So here there are zero electronegative groups. Here only one. Here there are two, and here there are three. So here three electronegative groups are attached. So that's why the delta value for this one is higher. It will be in this manner. So if we just plot the delta values here, so the delta values will be the order of this delta value. Let's give this one A1, 2, 3. So it will be in the order form 4, 3, 2, and 1. So the methane molecule, it doesn't have any electronegative group attached, so it has the lower delta value. So that's why the order will be in this manner, and which has the higher no, large number of groups are attached. So for this hydrogen, the delta value is most higher. So the exact value for this one, for first one, the methane shows the delta chemical shift value at 0.23 ppm. Similarly, the CH3Cl, in which this CH3 group, the hydrogens, it shows the delta value at 3.5 ppm, and in the DCM it shows 5.3 ppm. Similarly, the chloroform, it shows the peak about 7.27 ppm. So based on this one, you can solve the another problem from the assignment. Here is the concept of magnetic anisotropy, and so in which uh, the group which is let's have the example of this benzene one, benzene, or there are some other groups that I will discuss later. So here what happened, so we have the planar phenyl ring here, right? And to this phenyl ring there are hydrogens are attached. Let's say here the hydrogens are attached. So when you apply the magnetic field here uh, in the NMR, so the direction of magnetic field will be in this manner, right? So what happened? The magnetic field current generated in this manner here, and these hydrogens, which is like experience more de-shielding effect. So these circulating pi electrons, which are localized here in this blue one, they are located around the ring current will be located in this manner, and the induced magnetic field will be reinforced on these terminal hydrogen atoms. So this hydrogen experience the again more shielding effect on this protons which is attached to the benzene ring. So that's the reason if you look at the values in the olefinic for the olefinic protons, which is let's say we have some example of these olefins, and these protons will shows the delta value nearly. This shows delta value nearly 5 to 6 ppm or 6.5 ppm delta values for this one. But for the aromatic one, we have seen the examples which in the aromatic one, these aromatic protons which shows the delta values in the range of depend on the R group, they shows around 7 to sometime up to 9 ppm. So that because of this magnetic anisotropy. So here, this proton shows the induced magnetic field reinforce the external magnetic field B0 near to the protons, which are that deshielded. So this is the induced magnetic field, and these protons are near to this induced magnetic field. That's why they experience the deshielding, and that's the reason the delta value for the aromatic protons uh, are higher compared to these olefinic protons. Although aromatic, these are the olefinic protons only, but they are aromatic because of these aromatic protons, and they show the de-shielding here. The another example for this one is like here, I will show the example of acetylene molecule in the or acetylenic proton. So this acetylenic proton, which I have shown in the blue one, which has let's say any R group attached here. So this proton, what happened in this one? Let's I will draw in the vertical manner this one, this R, and here H. So when you apply any magnetic field here, magnetic field B0. So in this way, in this also, so in this manner, the induced magnetic field will be right. So it will be direction will be in this manner. So but here, which is like they are in the shielded zone, and the zone, this blue one, this is like this region with this shielding zone, and this zone here above and below, it is like shielded zone. Here more and more the density will be higher in this one. So that's the reason these protons shows some lower delta value than it should be. So if we have example like CH3H, or let's say CH which has attached to the double bond H, and again the C triple bond C H. So the if you look at the electronegativity, so this carbon which is like alkyne, which has a higher electronegativity, but still this proton will have the lower delta value as compared to these protons of the olefins or the double bonded one. So because of this magnetic anisotropy. So here let's say here the one example uh, they shows the delta value of around for this double bond or triple bond around 2.5 ppm. But for olefins, as we have earlier seen, it shows about 5 to 6 ppm or 5 to 6.5 ppm. So this is the effect of magnetic anisotropy. Similarly, uh, here there are example of aldehyde group. So if you have example, let's say take in the another one. I'll just introduce one slide here. So we have example of aldehyde. So this aldehydic proton are de-shielded protons compared to the normal protons. Similarly, highly deshielded, right? Similarly, the benzene protons, they are also highly deshielded. And this proton, which is like olefinic proton, they are shielded. So these three, four example you need to keep consider. These are the olefinic protons. They are as usual, they are deshielded one. But this exceptional case of the alkyne, they are shielded because of the this magnetic anisotropy. So this is general regions that we have seen earlier also in the last session of the problem solving session. These are the alkanes or the alkyl protons. They shows here in the range of 0 to 1, right? These protons are like from 1.5 to 2.5. Let's say we have here the in this one we have here oxygen or any other nitrogen or any other group. So they shows these protons, which is like alpha protons, to the electron withdrawing group. They are located around 1.3 to 2.5. Similarly, if the proton that they are directly attached to the carbon, which is attached to the electron withdrawing group, like let's we have the seen the example Cl, and we are considering this hydrogen. So if you are considering this hydrogen and let's say any R group, so these protons lies in between 2.5 to 4.5. So we have a methoxy group, let's say. So CH2O CH3. So this methoxy and here are this methoxy and this CH2, they locate in between 2.5 to 4.5 here in this region. Similarly, these olefinic protons, they are from 4.8 to 6.5 in this region. And the aromatic protons, they based depends on the R group. If you have electron donating group attached, then they shift toward the 7.5 or some 7. And if you have the electron withdrawing group attached, so that time these aromatic protons will be located up to 8 or sometime 8.5 also. The aldehydic protons, they shows uh, the signal between the 9.5 to 10, in between 9.5 to 10. Also, sometime the uh, beyond 10 as well. And the acidic protons, so these acidic protons, they lies in between 9 to 12. So they are mostly shielded protons. So this is general region that you need to keep consider. So I have just tabulated here the delta values, and so this delta value you should keep in remember. We have example like methyl group, so 9.9 to 1. Let's say we have CH2 group which is like attached to the R, so 1.2 to 1.7, and we have the three alkyl groups attached, and then this we have to check the CH value. The CH proton shows in between 1.5 to 2. Similarly, we have the methyl group attached to the olefin, which shows 1.5 to 1.8. Then we have the RNH2. This nitrogen, the protons attached to the nitrogen, which shows in between the 1 to 3, in between anywhere they can locate, depends on the R group. Similarly, the protons which attach to the aromatic ring, the methyl group which attach to the aromatic ring. Let's say the example of the toluene. So they located in between the 2.2 to 2.4. Similarly, we have the the proton attached to the carbon, triple bonded carbon. So they show in between the 2.3 to 3 ppm values. Let's say we have the example of methoxy group. So this methoxy shows in between 3.7 to 3.9. And we have the ester, then that time it will shows in between 3.7 to 3.9, the similar same region about. Another example is like alcohols. They can show protons from the alcohol, they can show in between the 1 to 5 delta values because of this OH. So if you have hydrogen bonding is stronger hydrogen bonding, the delta value is just near to the 5, and very weak hydrogen bonding in between the two molecules, then it will lie in between the 1, nearly 1 or 2 sometime. Similarly, if you have the protons which are attached to the olefin, that is double bonded carbon atom, which shows in between 3.7 to 6.5, depends on the R groups. So if you have the R is equal to O oxygen, at the time this delta will be near to the 7 or 4, near to 3.7 to 4.5 in between. And if the R group is like alkyl chains, that time it will be in between 5.5 to 6, in that range. So if you have the amide protons, which lies in between 5 to 9 ppm value, the aromatic protons, they in the aromatic region 6 to 8.7. These are the approx region where the aromatic protons can lie. Depends on the groups attached in the aromatic ring. Similarly, we have aldehyde, as we seen earlier, 9.5 to 10. Hydroxy, which is around 10 to 13 or 9 to 13 or 9 to 12, in between that region. Right. So in this, these are the some common values that you have to keep noted when you are solving the problem based on this one. Here it's one the problem based on some another concept. So the I will take directly the question. So there are two chemically inequivalent coupled protons. So we have two chemically inequivalent protons. Let's take example this proton and this proton, right? And let's say we have different R groups attached here, right? Inequivalent, right? Couple, they are coupled, so they are coupled to each other. So it should be adjacent, right? Or maybe in the if it is in the aromatic ring, then it this we have seen, right, the ortho meta para coupling. So here, so they can be any between these two. Let's say these two protons, they are chemically coupled with the chemical separation between the two are 2000 hertz. So they are separated from each other by 2000 hertz between them. So the coupling strength, so the J value is 10 hertz, right? So let's say this is the delta TMS, and they separated they separated from each other. Let's say let's take this instead of ppm. Let's take this in the hertz value, and one lies here and another will be here. One hydrogen, another hydrogen. The coupling constant is like 10 hertz, gives rise to the multiplicity of the peak, the total number of peaks detected, and their intensity. All right, so we have two protons. We have to consider only two protons, and these two protons are coupled to each other. So, so the splitting due to, for let's say, take the example of first one HA. So because of this another this proton, this will show a doublet, right? So it will show the two peaks. The another protons also can show the similar manner. So we have the HB, and this can also show the splitting due to this can also show the splitting due to this another HA hydrogen. So in this manner, the similar as like HA, it shows the two peaks with the intensity 1:1, and similar manner, the HB can also show the similar uh, coupling and with the intensity 1:1. So in total, how much total number of peaks detected and their intensity. So we'll detect the four number of peaks and with their intensity. If you compare the intensity, so this first two will be in the 1:1. Similarly, these two are also in the 1:1 ratio. And since these two protons are these peaks are due to only one hydrogen, so this should be equal. So in this way, the intensity overall intensity will be 1:1 S21 S21. So we get the four peaks with the intensity. They are all one equivalents. So equal intensity. So that's why. So the intensity will be the 1:1 S21 S21. So in this way. So the four peaks here. Another example is the number of magnetic energy states expected for four protons are coupled among themselves. So let's say we have the n number of protons. They couple themselves. So it will be how much it will be? It will be 2 raised to 4. So the whatever the answer it come, so the answer will be that. So in general, you can keep the consider uh, the magnetic energy state for possible for any number of, so any here is equal to 4, right? So that's why uh, this 2 raised to n, this formula you need to take consider. So to find out the magnetic energy state possible for the protons which are coupled among themselves. So the total magnetic energy states for this one will be 2 raised to 4 in this way. So any doubt here up to here?
No, sir.
All right. So in this way, you can solve this problem as well. Another example is based on the same intensity. And let's say we have taken here example of this molecule, the structure you can see here. And you have to find out the number of peaks in these molecules as well as their intensity. So we need complete analysis here. First is number of peaks. Just total number of signals. Second, uh, their intensity. So how many types of protons or chemically equal protons are present here? It is already given here. So no need to discuss. But yeah, so this is HA and HA1. These both are chemically equivalent protons. So we get the setup because of these two hydrogens, we'll get one signal, and because of this HB, this is HA, right? And this HB, this is one HB, so we get another second signal. So you get the two signals, right? Because two types of protons here. So we will get the two signals before coupling. So if we check the coupling of these protons, this so this HB can couple with this HA in the similar manner. This HA can couple with this HB. So let's take the example of this HB, and if you check the how much how it will be show how the peak look like for this HB. So we have here one and two hydrogen coupling hydrogens, right? So the signal for this one will be n plus one, right? So splitting for this one will be three. Am I right? Because we have two protons. And how the intensity for this one looks like? 1s2, 2s2, 1. You have seen in the videos, right? The how the intensity will be get for this one.
Yes, sir.
Yeah, because we have the two protons right here. So if we, I will show only roughly. So we have the this HA, sorry, HA. So HA coupled with the HA1. So how it will be? It will be show initially, let's say like this doublet. And since these are the also HA, sorry, HB can also couple with HA2, right? So this is due to HA1, and this is for HB. Now again, in this manner, so it will be add up right here. So this intensity, let's say this splitting is due to now HA2. So overall intensity for this peak will be 1s2, 2s2, 1. So in this way, because this coupling constant is same, so this will get add up here, and the intensity will be like this here for this one. So 1s2, 2s2, 1. So this HA proton will show the intensity. It shows the triplet with the intensity 1s2, 2s2, 1, right? Similarly, if you calculate for, if you do the same for the this Hb2 set of protons, I'll just rub this all stuff. So we have the another set of protons like Ha, and let's calculate for this now Ha. 1 and 2, both because both are chemically equivalent, right? So because of this Hb, this proton will show doublet, right? So and the intensity for this one will be 1:1 here. So we get like this doublet for this Ha, and similarly for this one, how it will be? It will look like this one, 1:2, 2:2, 1. So in this way, we get the signal for this one in the NMR, 1H NMR spectra. So any doubt in this one? So
Uh,
we'll check.
Hello,
Yes.
hello.
Yes.
Sir, what happen in case of three equivalent hydrogen atom in the adjacent carbon?
All right. So let's say we have here instead of chloro, there will be hydrogen, right?
Okay, sir. Yes.
In this example you are talking about, I will take fresh example.
Yes, sir. Yes, sir.
Right, the same example that I have shown here, right? So here, let's say we have example of here Cl2 and one hydrogen is attached. Similarly here CH3, right? So three hydrogens are attached. All three are equivalent. So I have just kept here uh, in the one set. So we have three hydrogens here and one hydrogen here. So this is the example. And we want to now we have to do the first similar manner, number of signal, and second the intensities of each, right? So we have here, let's take the example, this is Ha and this is like Hb. Now check for Ha now. So we have three hydrogens, right? So n plus 1 peaks will be there. So how much it will be? It will be 4 peaks. And how the intensity for this all this quadrate will be? We call it as a 4 peaks means quadrate. We call it as a quadrate. In the previous one, here for this one, there this 3 peaks. So these 3 peaks. So we call it as a triplet. This is doublet. So in this one, it will be quadrate for this hydrogen Ha. And this one, this will be in this manner. And all the four, it will be like very like this way. So the peak will be look like this, and there will be, yeah, you can just draw here. So this quadrate will be looks like this. All have equal intensity. So this quadrate will be like this for this Ha. Similarly, if you look at this for this CH3 group, that Hb, Hb is due to three hydrogen, right? And these three hydrogens coupled with this only one hydrogen. So it will show how much? N plus 1. So here n will be the here coupling partner. So here n is equal to 1, right? 1 plus 1. So it will show only doublet. So like this way. So here we'll get for these three hydrogens, we get only doublet of three hydrogen. And here this will be a quadrate of one hydrogen. If you take the integration of this one, that part we will see the later case. But if you take the integration, it will be one hydrogen. And if you take the integration of this one with respect to this one, it will be three, like this way. And if we check the intensity of this one, this will be the 1:1, this doublet. Similarly, this quadrate will be all of the equal intensity, like this way. Any doubt here?
No, sir.
All right. So we'll see another problem here. Oh, somehow that part need to. I'll just stop sharing. Somehow it's like. So if you have any doubt regarding this one, we'll solve more problem now. I will take some few problem based on this one again here. Just open some another. That presentation got stuck somehow. So I will check another. All right. So is this screen visible? There are some technical glitches here. So yeah, we have another problem. I'll just take the problem directly here instead of taking it from there. All right. So we have the structure. I will take the structure there. Yeah, we have the example here. CH2. Let's say you have here CH2 as CH3, CH2, double bond O, CH2, and CH3. So we have one group here, and that in this one, first question is the delta value order. And second question is, all right, first we'll see how the delta value order of this delta value here in this one. So let's say I will give the numbering. CH2, I will just extend some more chain. Right. So we have 1, 2, 3, 4, and 5 groups are attached. So, and the order of this one, the delta value order. So, which one will be the, let's say here TMS, and this value is up to, let's say it's up to 10, right? So, which which proton among this one will be the most shielded proton? And here this side will be deshielded. So here I have given the numbering 1, 2, 3, 4, and 5. So which one will be the most shielded proton here? So anyone have any suggestion here, idea? Which one is
First.
the right? This first CH3 protons will be most shielded proton. So the CH3 will be have lowest delta value, right? The next will be which one? Right here, just might be. I will just make it some clear here. Now which one will be the second one in the order?
Second one.
In this one, this methyl CH2 or this CH3 or this CH2? This
Second
CH2,
number.
this one will be here. Now, in between this CH2 and this CH3, which one should be the more shielded? Here we have CH3, which is directly attached to the carbonyl group, and here we have the CH2, which is attached to the oxygen atom. So, which one will be shielded among the CH3 and CH2?
Third one.
right, this CH2 will be shielded as compared to this CH3. So this order will be in this way. So this is as a label, it's not like a order, and this one, right? So in this way, uh, you can face some, you can solve such problem based on this one. The another question is, let's say we have the uh, any group like fluoro is attached to here, fluoro attached to the CH2, then we have the another CH2, another CH2, another CH2, and let's say we have the CH3 here. So here this fluoro is like electron withdrawing group. So the delta value also will be in this manner. As the length from the electron withdrawing group will increases, the effect will be decreases. So if you have the fluoro group attached, so the electron withdrawing group effect on this CH2 will be less as compared to this CH2. So this will be the so this first CH2 will be have the most electron withdrawing effect. So this will be de-shielded among the second one, then the third one, and the fourth one. So the distance effect of distance, right? On delta value. So here effect of electron withdrawing group on the delta value of the CH2 groups. So there are some problems in the assignment probably. You can solve using this one. I think we have covered most type of problems. So anyone have any difficulty in any problems from the assignment? Uh, I mean, you face any difficulty in solving this
Question
problem?
number
Which one?
10.
Question number 10. All right. So we have the question number 10. All right. The question number 10 is uh, one proton is coupled with two another chemically inequivalent protons. So we have one proton, let's say HA, and which coupled with the HB and HC, and also condition is that HB is not equal to HC, right? Which is chemically inequivalent. The molecule also contain 13C spin and nitrogen 15 spin. Then which of the following statement is true here? Right. The option A is there is possibility that all protons can simultaneously experience coupling among themselves. Right. Up to here is okay. And also with 13C and nitrogen 15 spin. Yeah, up to here this is also okay. So option 1 here looks too good, okay to me. So, but also we can see here, this can also be the MCQ or MSQ. We can also select multiple or one. But here option A is correct statement here. We will also look for the second option. What is the each proton can experience coupling only with another chemically inequivalent protons. No, it can also show with the 13C as well. So this is obviously the wrong statement. The another one is proton can couple only with 13C, not with 15. This is also wrong because this nitrogen 15 also NMR active, right? So this proton can also couple with this nitrogen 15. So, but here it is not mentioned. So this is the wrong answer. Wrong sentence. The another sentence is the protons cannot couple to nitrogen 15 because it's less abundant. No, but whatever the abundance for this one will be the nitrogen 15 has enough nitrogen 15 will be enough in this one. So this is also the wrong option. Here option A is the correct option because although let's take this example of we have these three protons. This one proton is coupled with this HAHB Also, there are in the compound there are carbon 13 as well as the nitrogen 15. So these both are also the magnetically active nuclei. So these protons can also couple with this 15 and this nitrogen also. So the option A here is the correct option in this one.
Sir, the proton themselves have couple. I not understand. Simultaneously experience
Right.
coupling among themselves.
Right. So let's say we have here, right, this one. As we seen the one example prior, which one is this example? So here, take example of this one. So here we have seen this Hb protons. This couple with this Ha as well as this Hb. Sorry, Ha1 as well as Hb1. Right. So that's why it shows the triplet with the intensity 1:2:1. Similarly, this Ha proton, they can also couple with this Hb protons and which show the doublet, right? So it is like it is not only the Ha proton coupling with the Hb proton coupling with Ha, but Ha proton can also couple with the Hb. It's like a two-way process, not one way. So the statement is talking about the same scenario. So here what mentioned, there are possibilities that all protons can simultaneously experience coupling among themselves. So this Ha proton, so this Ha, shows the splitting due to this splitting is due to Hb proton, and also this can also show the splitting due to, let's take the coupling, the the coupling constant different. So this can also show the splitting due to the Hc. Similarly, for Hb protons, this can show the splitting due to the Ha proton, also can show the splitting due to Hc proton. And similarly for Hc, this can also show the similar manner splitting like this way due to Ha as well as due to Hb like this way. So this is called, they can also show the simultaneous coupling among themselves. And also these are magnetic active. Also this HAB and HC, these all can show simultaneously coupling with the carbon 13 and the nitrogen 15.
Understand, sir.
Right. So any other
Question
question?
number 8. 8.
Mhm. Question number 8. All right. So question 8 is talking about, I'll just take the question on the screen. All right. So we have the question here. It is mentioned that the two protons A and X. All right. So we have the proton HA and HX with larger chemical shift separation are coupled with coupling constant 10 hertz. So when they show the splitting, so this will be 10 hertz. So this distance, this coupling between two peaks. So let's say here also, because of this HX, this can show the splitting and it show doublet, right? In the similar manner, this HX can also show the splitting, but here this splitting will be the same, right? So this distance in principle should be the same, 10 hertz. So this distance will also be the 10 hertz due to the HA. This splitting is due to HA and this due to HX. Right, these two protons with the larger chemical shift separation, they are coupled with the coupling constant 10 hertz. Three other protons, M, P, and R, are present in the molecule. Okay, we have another protons M, P, and R. Right. So HM, HP, and HR, there are three other protons are present, not coupled with any other protons. So they are not at all coupling with any other protons. So the number of peaks detected in the spectrum. So we have to solve this one. So we have already seen this HA proton and HX proton, they are coupled with each other, right? And the coupling constant is 10 hertz. That no need to consider because there are no uh, value related question. We just need to answer the question how many peaks will show in the NMR spectra, right? And this HA and HX, they are coupled with each other. So this will show two peaks, that is doublet. Similarly, HX can also show the doublet, right? So we get here four peaks with intensity. How much it will be intensity? This will be the 1:1. This will also the 1:1. And also there are also mentioned there are another three protons. Anyone have any doubt? Someone is speaking.
Sir, P, M, and R not give any P.
Yeah, they will also show the peak, right? So, but they will not couple with each other. This will not couple with each other, so it will get one peak only. This is also not couple with each other. This will also show one, and this is also not coupled with any other proton. So this will also show one peak. So there are three more peaks will be there in the spectra because of this M, P, and R, and also there are the four peaks due to this HA and HX. So which option here? The four peaks in the protons for HA and X, and four peaks for P uncoupled P, M, and R. This is wrong. This should be three, right? Four peaks for PM. This is wrong answer. The another one is two peaks for proton A and X. This is wrong because they couple with each other, so it should show the four peaks. Another is four peaks for proton A and X, and PMR do not give any peaks. This is also wrong. The last option is four peaks for A and X, which is up to here is correct, and one peak each. One peak each. That means there are three peaks, right? For P, M, and R. So the option D here is the correct option here. Any doubt here?
No, sir. Sir, if coupling constant's value is negative, then what affect to our spectra?
All right. It will be opposite. The pattern will be the opposite. Let's say we have the option. I will give some example here. Uh, do you have question in the assignment related to this one?
Yes, sir, seventh one.
All right. So we have the seventh question in the assignment. I will just go to there. All right. So this is the question. In principle, I should not solve the question based in the assignment, but we will discuss this one, and only difficult question we are going to solve. So this is the last question I am solving from the assignment. Don't ask another question based on the assignment only. Right. So we have a question here. The two coupling protons A and X give the doublet with the coupling constant plus 7 hertz. Right. Their chemical shift separation is 1000 hertz. What change expected in the spectrum if the coupling constant is minus 7 hertz? The first option given here, the spectrum remains unaltered, and the doublet transition is also the same at the same frequency. The B option is here, the frequency position of the two peaks of each doublet get interchanged. The C option is doublet separation of A and X spin increases by 4 times. This is obviously the wrong option. And D is the doublet separation get nullify. So we have here the doublet separation get nullify. This is wrong because the doublet will be there. And the C and D option is definitely wrong because it will not gonna 4 times because it's just negative value. Not it should not have any effect on the uh, And also, yeah, it is not going to nullify because it is not like a some kind of vector quantity to get the nullify, right? So we have the option A and B. So option A tells the separation remain unaltered, and the option B is the frequency position of the two peak of each doublet get interchanged. Right. So this is the correct option here. In the B option given, the frequency position of the two peaks of each doublet get interchanged because of this negative value. Otherwise, there will be no any effect. So let's say we have the two doublet due to A and X give the two doublet, right? So this is like splitting for the HA, and this is like splitting due to the HX. Initially, it is like, let's say I will give the number AB, and for this one, we give the C and D right here. So because of this negative one, only this distance, this 7 hertz or minus 7 hertz, this will not going to change the peak positions, right? Only this B can be this side and this A can be this side. It will be opposite, right? In this way. So only the peak, the frequency position of two peaks of each doublet will be interchanged. So this B will be here and this A will be here. So only this is the difference. There will be no any other difference in this inverse spectra because the 7 hertz value is constant. Only the sign is negative. So let's if initially it was like HA, HB, now it will be HB and HA. Only the opposite. So now it will be HB and HA. So the option B here is the correct option. So anything else in this in the problem based on this week course content? I think there are some more problems in my slides, but these slides, yeah, I think these are the only problems that I have. So hope you can able to solve this problem from the week 4. There are not much difficult problem here. Also, you can see the first problem that we have already seen there's some example based on this one, right? From the first problem. Also, we have solved the problem based on such problem based on the second question. Also, problem based on the not the exact problem, but we have seen the patterns like in this way, I think on this slide. So here we have seen the each and every delta values, how where it will be located. So I don't think they should face any difficulty in this one. Also, here the question usually where are the aromatic protons will be. So we have solved this question already. Similar questions, not this exact question, but similar question. There are again here the fifth question based on the inequivalent coupling protons. I think we have solved such problems. So I don't think there should be any problem to solve this to solve the assignment.
No, sir.
Right. So if you have any doubt, you can ask me right now, or else uh, any. Right, we don't have any problems here. I will just stop the recording. You are able to find the recorded session in the link, right? So I think we'll stop here for today. So thank you so much for joining.
Thank you, sir.